Hi, welcome to this introduction to transcranial electric stimulation. Of all brain stimulation techniques, electric stimulation might be perhaps the most intuitive technique or intervention for brain stimulation. Our brains, after all, are for a large extent electric organs. This has been known for a long time. Look at, for example, ancient Egypt or ancient Greece, where they were using electric fish as a treatment for debilitating migraines. I don't think I would recommend this. Perhaps many of the patients back then were miraculously cured before they were receiving the electric shock from the fish. Now, a little bit more scientifically, it's already a few hundred years ago that we were learning that many of our muscles and other body parts were electrically innervated. Consider, for example, the frog legs that start twitching when the voltage is applied, or slightly more gruesomely, decapitated victims, often murderers, whose bodies were still responding to electric stimulation. But a real breakthrough is in the last century, where Wilder Penfield were using direct electrical stimulation on the cortex to map out different functions during a surgery. And this is an approach that is still in use every day for neurosurgery, to know which brain regions to spare and which functions they serve. But it kind of requires that you open up the whole skull to be able to deliver that current on the brain. Now, and it was in the 80s when Merton and Merton, actually you can see both of these in the picture on the right, they're giving a lecture just like me here. They're using a high voltage stimulation over the motor cortex, and Merton, the one sitting here, is pointing at his hand that is twitching. So let's zoom in actually. You can see even on the back of this slide, you see the very simple electric diagram, and in the front you see the stimulation, and you can see this lecturer sitting there very calmly. That's because he had a bit of practice. Electric stimulation at high voltage, it hurts. Sure, it penetrates through your skull and it stimulates your brain, but it's not really recommended. Using a current either running in a positive or a negative direction, actually the anodal and cathodal currents. And what they were showing is that they can modulate the spontaneous firing of the neurons in the brain, either upregulating, as you can see for anodal stimulation at the top, or fewer, downregulating at the bottom for cathodal stimulation, as we call it. And this truly is neuromodulation. The stimulation, namely, the electricity, isn't itself strong enough to elicit all those action potentials. No, you're modulating spontaneous activity. You're making it more likely to happen out of itself, or less likely. And that's what we mean with modulation. If we're modulating the spontaneous activity, you can also envision it might interact with many ongoing processes in the brain. A process such as learning or plasticity. So what we see at this plot, and it's already quite a few years ago, we see brain activity, and then there are at the top one, there are two blocks of anodal stimulation, and after each block, the brain activity is upregulated. You've given it a push in a direction to increase its excitability. This is a plastic effect, an early phase plasticity, and we might also call it a delayed effect. Stimulation happens during the black time periods, but the neuromodulation happens a little bit longer. And at the bottom, you see what happens for cathodal current running here. So that's in the opposing direction, and now the neurons are not upregulated, they're actually hyperpolarized, so they're less likely to fire for a longer period in time. This is with direct measurements in animal models. Those are not always available, hopefully, in humans. But the technique, about 20 years ago, has been translated to human applications. And it looks deceptively simple. We have a very simple circuit. There is just some current running, and actually it is 2 9-volt batteries in a row. That already would be enough. And this is applied with, well, it started out with just 2 electrodes. One is positive, the other is negative, the anode and the cathode. It does matter where on the brain we place them, because that's how the current will be running through. We can have a look in the lab. Here we see actually the professor and back then postdoc. This is Walter Paulus and Michael Nietzsche. And you can see how they're applying these electrodes on the poor postdoc. It's actually his research though. And they are probing the brain excitability. There's a trick they need to play. I've just said this low voltage transcranial electric stimulation of itself, it doesn't elicit action potentials. So how do you know that it modulates the brain activity without being able to measure inside the brain? Well, the trick they're playing, they're going to use transcranial magnetic stimulation. You can see that he's holding the coil to evoke a muscle twitch in the hand. That's why you can see the hand in the picture. And if the muscle twitch is becoming bigger because of the electrical stimulation, that's an excitability. If it becomes smaller, that's a reduction of the brain excitability. And this 2-directional effect is what they observe depending on the direction of the current. Right? You can see the anodal current increases the excitability, and the cathodal current, negative here, that decreases the excitability. But it matters where you're placing these electrodes. In fact, for this study, they tried out many other parts in the brain. You can see all the combinations of the different positions. None of them worked except the specific montage where one electrode is over the primary motor cortex and the other actually is here at the front. It's over the primary motor cortex that we have a lot of current going in, and that's why we have a modulation of motor activity. In the rodent work, we saw that such stimulation has longer lasting effects, right? So it modulated early phase plasticity. Let's look what happens in humans. Well, this stimulation, both anodal up and cathodal down, modulates with only a few minutes of stimulation also the brain excitability for a few minutes afterwards. And if we stimulate for longer, we can also see that this effect lasts for longer. We're not really changing the brain permanently, right? It always goes back to baseline, but we have a plastic effect, a delayed effect, which duration depends on your stimulation parameters. And after this introduction of actually a translation of this technique from animals to human application, it has exploded with many different patents. So far, we've only been talking about the direction of the current, and this is often called transcranial direct current stimulation, TDCS. Right? We have a direct, it's only in one direction, and that's what you can see plotted here on the top left. Others are saying, well, we can also give it another shape. We can have an oscillatory shape, transcranial alternating current stimulation. And that might be a shape that's more directly related to brain waves that we would see in a healthy human brain. But in many cases, there are hypotheses on how it modulates with the probability of action potentials, as you can see in the bottom. And if we're changing the probability with an oscillatory shape, you might think that we're really entraining oscillations in the brain itself. So the brain starts firing in the same rhythm as your applied stimulation. Or maybe we are modulating brain waves themselves. And that's what you can see at the right bottom. There are many more ways on how to shape your electric stimulation. In fact, some people have suggested we can apply stimulation at random, so going up and down in all random frequencies. And you have all frequencies present, and you might think, wow, what are you doing? Maybe you're just adding noise to the brain. That's ridiculous. But that's the whole idea. Adding noise to the brain can have very beneficial effects. Right? One of the models of transcranial random noise stimulation is a principle of stochastic resonance, where adding a little bit of noise makes subthreshold signals suddenly suprathreshold and visible. Too much noise just disrupts the whole system. I completely agree here. But there is a balance on just Goldilocks enough of the noise. In some of the other lectures, we'll go deeper into these mechanisms and start exploring the whole world of different shapes of transcranial electric stimulation. But what's critical for now is that we realize that this technique is mostly used to induce plasticity. Right? It's a modulatory technique, and imagine that there are, in a circuit, there are action potentials firing. Some are many neurons together, others are fewer neurons. It's a bit weaker, the signal. But a few of those times you cross a threshold for where the brain circuit says, I need to learn, I need to change, and long-term potentiation threshold in this case. If we give this spontaneous activity a boost with the n-nodal TDCS, then suddenly all of these spikes cross the threshold and we have a stronger plasticity signal. This is called gating synaptic plasticity. And you can imagine that we also have the reverse. If we modulate it in the other direction, we might make it less likely. Actually, now we might be inducing long-term depression, which means that activity is decreased or inhibited for a longer period in time. Brain stimulation can interact with ongoing brain signals in quite complex ways. And it means that people thought if we can also use it to enhance brain performance. This is tricky. It's not right? It's not easy to write in the brain and say which direction that it has to go. But the modulatory technique, you can envision actually that people are using it to give the learning a boost. Well, in this specific study, they thought, let's add that little bit of noise giving the plasticity a boost. And they said, let's do something that everybody can, although they might not like it. It's learning maths problems, calculation problems. They were having two different types of problems. One where you really have to think, you have to learn new math operations, the calculation problems. Another are just repeating the numbers. Those are drill or drilling problems. Compared to the control stimulation in red, the transcranial electric stimulation in blue really made people better in both of these problems. They learned better to become better calculators, and they learned also to better repeat, to drill the numbers. Does this have a long-lasting effect? Well, to answer this question, they invited these participants back into the lab after 6 months and actually observed that the beneficial enhancing learning effect that happened for calculation problems stayed on for 6 months. People really had learned to get better at these calculation problems. Not at the drill, that there's hardly something to learn there, right? It's just getting faster at repeating. But it showed that there might be a possibility to enhance learning in the brain by combining it with transcranial electric stimulation. Many people got excited about this idea, and there is a large literature. But luckily, it also invited many people to critically reevaluate what is happening. Because even this might sound a little bit magical. Are we really enhancing learning just by placing 2 9-volt batteries on the head? Is that really feasible? So people started looking or making overviews of the literature, and they were saying, well, we really have mixed evidence, and others were arguing, maybe there isn't even enough current to go in the brain. Maybe you just feel the tingling on the outside, and that is enough. Others were even recording. This is a cadaver recording with electrodes where you can see which current is really going into the brain when we're applying it on the outside. And they were saying there isn't even enough current at all. Now, this is the beauty of science, where people are arguing for and against, and together they are learning and increasing. It turns out that actually using a dead body with a dead brain might not be the best model for a living and active brain. When we're talking about neuromodulation, even very low currents can be enough to slightly bias the spiking probability. But it has made a very positive impact on the field. Namely, we are starting to model exactly how those currents are going through, that if you're running your study and placing your electrodes, you're really sure what is going on, and that you can predict what the effect and the strength of the effect might be. Now, this is all based on physics. You don't need to grasp all of these parts. Maybe you're comforted to know that the currents are so low, they're well below what you need to actually damage the brain. But you might be a little bit shocked to see that if we running such models, most of the current is actually running through your skin. It's not even entering the brain. And then when it enters the brain, it's quite diffuse here on the skull. And in the brain itself, these big electrodes are quite dispersed. It is almost with these big patches as if you're stimulating half of the brain. The brain is folded in complex ways, and it matters which direction the current is going. But it is really pushing the field forward to consider maybe not a one-size-fits-all, but an individualized approach for brain stimulation. Because everybody's brain is different, everybody's skull is also different, and yet for most of our brain stimulation studies, everybody is receiving exactly the same intensity, maybe 2 milliamps. But our brains are so different, and you can see here in the modeling that even though you have a fixed intensity, and those are the two vertical lines, there's a wide spread of the electric field that is experienced inside the brain. So some are arguing to individualize this. Maybe we should titrate our electric stimulation on the outside so we have a more uniform stimulation in the brain. These are exciting ways in how the field moves forward. It hasn't really trickled back into applications. Namely, across the globe, transcranial electric stimulation is so cheap, it's 2 9-volt batteries after all, that there are a gazillion companies who are selling it and promoting that you're getting much better at gaming or attention or treating all kinds of disorders. And sometimes it's quite contrasting to see how we would run our research in the lab. For example, if we're running our simulations, we notice that these big electrodes might also stimulate half of the brain, but we want to be specific. So now, rather than 2 big electrodes, we're placing a small one in the middle and a ring one on the outside. Right? This is what it looks like. We have electric paste, and we carefully place it on the participant's head, and we're running models, and now you can see that we have a much more refined and constrained stimulation site. Also, rather than just dumping electricity on the brain, we're really shaping it in the same way as brain waves are shaped, with nested and complex oscillations, brain waves going up and down. It allows us very tight controls, and it allows us stimulation across 2 sites, bringing them closer in coupling or further away. Well, this is quite a fair contrast, far removed from what is happening in therapeutic transcranial electric stimulation, or what you might buy on a commercial product to improve your attention or gaming speed. But it is the direction that the field is moving, very specific interventions. So after this overview, you have learned about an historic development of transcranial stimulation already from the ancient Egypt, about the electricity of our brain, about the interventions that we've used both to open up the skull and have direct stimulation on the cortex, informed by animal models and animal research that has now led to a translation in human applications. And I've talked about how many of these protocols are actually used to modulate plasticity, to have longer term effects. And that gives them a large potential not only for research, but also for therapeutic applications. Thank you very much.